Welcome back to the channel. In today's video, we are diving into an important topic in digital electronics and computer science. So, ones and twos complement. These concepts are essential for understanding how computers represent and handle negative numbers in binary form. By the end of this video, you will be a clear understanding of how unsigned and signed binary numbers work and how to perform ones and twos complement operations with easy using both shortcut and detailed methods. So mainly what is meant by ones and twos complement and its usage. So basically we can use, so we will see the usage in the upcoming videos. So now currently let's discuss what is meant by ones and twos complement in this video. There are two types of binary digits. So first one is unsigned binary numbers and second one is signed binary numbers. Let's see what is meant by unsigned binary numbers. So in daily we are using the normal binary numbers, so without their negative sign or with only with just magnitude. So that is known as unsigned binary numbers because we do not consider the magnitude of the number, we only see the positive number. So that is unsigned integers or binary unsigned binary numbers. So now onwards we will see what is meant by signed binary numbers. So in decimals we use plus and minus to represent positive or negative numbers, but in binary we do not have pluses and minuses. So we use only zeros and one notation to represent the same as negative or positive numbers. How? So we will see deep in the further upcoming video. The most significant bit or the MSB bit, that is 0, so the whole digit is positive. So if MSB, the most significant bit, is 1 for a 8 bit of a binary digit, then it is negative. Let's discuss. There are three types of methods to calculate the negative or to differentiate between positive and negative. So in signed binary numbers, so those three are signed magnitude form, ones complement and twos complement. I think most of you heard about ones and twos complement. So I also wrote there helps to identify the positive and negative numbers in binary system. So let's start with signed magnitude form. So the first one is signed magnitude form. So if you see, consider an example. So if you see an example, then you can able to understand it very clearly. So if you consider 34 a decimal number, so if you want to write that in 8-bit decimal to binary form, so that is 0 0 1 0 0 1 0. So the red highlighted 0 is known as most significant bit. So that is only 0, means that is positive. And the most significant bit for the minus 34 is 1. So you have to by heart or you have to recall that plus means 0 at MSB, minus means 1 at MSB, and the remaining all the digits will be same for the plus and minus. So if you consider the second example, that is 52 in 8-bit, we can represent like that. So I hope you know how to represent in binary to decimal or to decimal to binary. If you don't know, so you can check our previous video that I am giving in iCards also as well. You can check the description as well. So that is plus 52. So similarly we can able to calculate minus 52 also. Nothing is there, the red color highlighted 0, you have to change to 1, that's it. So that's a representation of plus and minus. So if you consider the plus 0 in 8-bit, so it is represented as 0 and 7 zeros. So because 8 bits now, so we have to fill first bit, the 8th bit 0, and next 7 bits will be zeros. So similarly if you consider the negative 0 in 8-bit, so it will be 1 and remaining and 7 zeros. So it's, if you consider the range of any n bit, so it is ranges from minus 2 to power n minus 1 minus 1 to 2 power n minus 1 minus 1. So this is the given range of any bit. So if you consider an example, you can able to understand. With the help of formula, let's see an example with n is equals to 4. So with n is equals to 4, I have put in that formula. So I have obtained from minus 7 to 7. So basically if n is equals to 4, so we can able to go from minus 7 to 7. So basically in that two zeros are involving. Let's see in the next slide, then you can able to understand that. As you're seeing there, so plus 6 and minus 6 and plus 5 minus 5 plus 7 minus 7 like that are there. It's not a problem. So it's our requirement only, but unfortunately we are getting plus 0 and minus 0 as well. So this gives an error while calculating something, or in computer architecture also it may give some errors. So we don't require like this. So we only want 1 0, that is plus 0. So this method is not much used for the calculations. So let's see the 1's complement. So how it provides, we can check once. Let's consider the 1's complement. So if you consider the 34 in 8-bit, so 34 can be represented as like that. So if you just invert all the bits with zeros as ones as zeros, so that is only our 1's complement. How that is possible? So let's see. But why opposite or inverse of binary digits is the 1's complement or negative of the binary digit? So plus 34 given, or we know that. So simply by inverting all, we are getting minus 34. Is it possible? So if you write the decimal format of the down one, minus 34 one, so it is not equivalent to that one, not equivalent, it is coming other than 34. So how it is possible? So let's check. So for 1's complement, this is the formula, that is 2 power n minus 1 minus 1. So if you consider an example, that is 12. So if you want to represent with the n is equals to 5, that means 5 bit. So if you keep n is equals to 5 in the formula, so you are going to get, so 32 minus 1 minus 12. So you should not do directly the minus. So you have to convert that as to the binary format. Then after you have to subtract. So I have highlighted with an yellow circle. So that is our final answer, that is our 1's complement. You can also cross check that which is the normal 12 as binary by inverting it. So if you want to convert 12 into 1's complement, so you have to write first 12 into binary. So 12 into binary is equals to 0 1 1 0 0. So just invert it. So after inverting, we are going to get 1 0 0 1 1. So that is our final answer. So that is just inverting by that's a 12's binary. We are getting that just inverting. So with the help of formula also we are getting that only. So with the help of formula we are getting 1 0 0 1 1. With the help of just inverting we are getting 1 0 0 1 1. So by this what we are understanding is that by just inverting we are getting the output. So no need to take stress or apply the formula, but it's better to recall the formula if you know much about 1's complement. It will be very useful in others also. If you consider the range of the 1's complement, so it is given as same as the sign magnitude form. So that is given from minus 7 to 7. The formula also same, minus 2 power n minus 1 minus 1 to 2 power n minus 1 minus 1. So if you consider in this also, you are able to see the table. So in the table we are going to get 4 zeros in binary representation. In 1's complement we are going to get just inverting the 4 zeros. So that is 4 1's. So in 0 also we are getting 2 different digits. So this may also cause errors while calculating precise calculations in computers. So we don't need 2 0 values. So this 1's complement is also not mostly used, but it is also one of the method to convert into a negative numbers. So let's see the 2's complement. So 2's complement is the most used by all because in that only 0 has only one notation. Let's see that. There are two methods to calculate 2's complement. 2's complement after finding, what we are going to get? The negative of the number only. So all these three methods are, we are going to get that negative of the number. So let's see what is meant by 2's complement. So if you consider an example of 34 in 8-bit, so just invert it. By inverting, we are going to get 1's complement. So that we already saw in the 1's complement method. So the basically 2's complement is nothing, just 1's complement plus 1. That's it. So 34 after 1's complement we are getting, so we have to add 1. So as you are seeing there, 7 zeros 1 1. So that is in 8-bit. So we are going to add the 1's complement with 1. So the final output, that is 1 1 0 4 1s and 0. That is our 2's complement. That's it. So this is the one of the method, simplest method. So this is also second method. The second method is very easy than the first method. By seeing only you can able to identify with the second method, the 2's complement. So basically I have written the 34 in 8-bit. So just normal 32 in positive I have wrote there. So start with the least significant bit, or with the rightmost, the right hand side, the rightmost side. So start going right to left. So while you are going, if all zeros are happening, so don't change anything. So start changing at the first one happens. So in my case, first 0, so don't change in the output. So next one is coming. So after 1, what are the digits? Don't care them, just invert all of them. So that is our final answer. So if you consider in this case, so 0 not changed, 1 not changed, 0 change it to 1 0 1 0 1 1 1 0, and last two digits also changed. The most significant bit, the red bit also be changed, has to be changed. All are zeros, don't change. If all are 0 and last bit is 1, so only change the last significant bit, the last bit, that is most significant bit. So if you consider the formula also, that is 2 power n minus n. So if you consider an example 34, so you can simply with an 8-bit you can simply just subtract and you can able to get the answer. Yeah, you can try by your own. Another example, that is 60-bit, that 60 in 8-bit. So minus 60, try to convert as minus 60. So okay, that's you try your own examples as well. So like that, in between any numbers like 54 random numbers, you can try your own numbers as negative numbers, try to change. So if you consider the range of this 2's complement, that is minus 2 power n minus 1 to 2 power n minus 1 minus 1. So if you observe in the first term minus 1 is not there, so that the final answer for n is equals to 4, you are going to get minus 8 to 7. So that's it. With this clarity you can understand there is no negative 0 term in this. So this is the most widely used because there is only one 0 term. So this is the most precise one. No error, because no errors will be coming because only one term of 0. So the ranges of three things, the sign magnitude form, the 1's complement and the 2's complement. So the ranges you have to remember because it's very important. So in this also it's important. Thanks for watching up to now.